now talk about data and its transformations. My goal with this presentation is to highlight the benefits of functional programming and the data-driven approach. I found that using this way of thinking results in higher quality code and more reusable components. My other goal is also to motivate you to adopt these ideas in your own work. And I'll be showing some examples which are written in Swift, but they can similarly be implemented in Kotlin and yeah, probably other languages as well. So I want to briefly introduce myself first. I started programming when I was in middle school. Around 2001, I got interested in web development and ran my own website. Then in 2008, I went to Canada to study computer science at the University of Toronto. And shortly after my bachelor's studies, I got interested in iOS development, and I had an idea for my own iOS app, which I published. Then prior to joining DevExperts, I worked on a white label mobile banking application, and last year I was involved in the overhaul and redesign of the DX Trade white label app for iOS. So the main ideas I'll talk about are discussed more in depth in a book called Domain Modeling Made Functional. This is what the book looks like. And so the author has done a couple of talks that teach functional programming, which I highly recommend. And if you scan the QR code, you can find a page with more links and information with articles and links to the videos. Okay, so I'll start with an overview of the expression problem, and yeah, this is just a small example of working with geometric shapes which illustrates it. So on the left, I'm implementing this with a typical object-oriented approach, and on the right, I'm using a more functional approach. In the object-oriented approach, it makes it easy to add new types of shapes, but it requires more work if I want to add new functionality, so new functions. And with the functional approach, it is the opposite. So adding more functions is just as simple as implementing them. But yeah, if I want to add new cases of shapes, then that requires changing each of the functions that I have. And so there's one more thing that's worth pointing out, which is that the area methods that circle and square implement actually receive an implicit parameter. And so because of that, these methods work in a very limited context. So if you contrast that with the area function on the right, it actually works for all kinds of shapes. And because of this, it is much more generic. So Swift enables us to add generic functions on types by using protocol extensions. And this is an example of building onto the shape protocol. So protocol extensions make it possible to basically to flip to the other side of the expression problem and easily add behavior to classes and structs. Yeah, this could even be done for protocols that we import from other modules. So yeah, basically protocol extensions can be a useful feature of the language. Okay, so I will switch gears now, and I will talk about cooking for a bit. So this is the recipe for pancakes, and I can use it to extract a list of ingredients and some of the tools that I'll need. But yeah, since I'm better at programming than at cooking, I'm just going to write a program that will do the cooking for me. So this is probably how a typical program to cook pancakes could look like. I don't know if you agree or disagree, but I think it looks pretty reasonable. And the reason I'm showing you is that for us as engineers, there are a few things that are important. So first, we have some mutable state. Second, there are some implicit dependencies between the function calls, and they aren't so obvious if we're just looking at the code. It is also not obvious if any of the tasks can be done in parallel, and there's also no error checking here. If you're going to add exception handling, then it will result in losing the nice overview of the entire process that we have right now. So the question is, how can we solve these issues? And I think it is useful to view the process in terms of data flow. And the way to start, the way to do that is to start by listing the most important ingredients. So I have this table here, and the first step is to sieve the flour, if we are going by the recipe. So basically, I need to implement this sieve function. Then in step 2, the output of the sieve function is combined with salt and is passed to the stir function. Then in step 3, the output of stir is combined with eggs, and meanwhile we can pass butter to the melt function, and this is something that we can do in parallel if we want. And yeah, so the process continues like this. I think you get the idea. So what's good to notice here is that if an error occurs at some point, it becomes very clear which tasks need to be redone. So that's very useful. And so based on this kind of thinking, here's how we can rewrite the original program. So it solves the issues that we raised earlier, and I think it is maybe a bit shorter. We could also spot trivial bugs by simply reading the code, because it is much better structured. And that means that we'll probably need to do less integration testing because of this. Okay, so we're done with the cooking. I want to show a more serious example. And this is this structure shows how the various order types are implemented in the mobile apps and the mobile gateway that we use. So this inheritance hierarchy gives an accurate representation of the data, but the thing is that it's quite complex. And there are a lot of functions attached to these types, which I don't really have the space to show here. So this makes it very cumbersome to make changes if we need different order types. And it is also difficult to work with when we implement the UI for creating new orders or modifying them, any of that. So here's how we could start to refactor this if we apply the ideas that we discussed so far. The first thing we can do is define all the types that we need. And these are just plain type definitions, as you can see. The goal here is basically to represent all the cases described in the business requirements. So each data type is related only to the data it represents, and there's absolutely no behavior attached. There's also no inheritance. Instead of that, we use composition. So you can see that the order group type actually includes the simple order types in it. And so moving on, we can continue by defining draft order, validated order, and submitted order classes. And they all conform to the order protocol. And yeah, these are the types that we're going to use in the functions that create new orders and work with them until the orders are submitted. So in this way, complex operations such as the validation can be broken down into smaller functions. So I can have a validate order function, which basically calls separate functions depending on each order type. So if you structure the logic this way, it makes it possible to divide like a complex process into smaller pieces, which can work together and support all the different types that we have. And it also makes it possible to have the type definitions and the logic that works with them in separate modules if we need. Okay, so talking about systems, I think Lego is a good example of a system that has well-designed individual components. Probably all of you have played with Lego at some point. But so the analogy I want to make here is that adopting a more functional approach in our work would enable us to write reusable components that work similar to Lego. So why would you want to do that? Writing code that's reusable, I think increases maintainability, quality, and consistency. And at the same time, it will decrease the probability of obscure problems and the effort to investigate any kind of issues that we come up with. So yeah, if such components are created properly, they will have high cohesion and low coupling. And so I want to spend a bit talking about this. I think it's useful to visualize cohesion and coupling this way as this two-dimensional graph. Yeah, so basically achieving high cohesion is crucial. If cohesion is lost, then the code base turns into a sort of a mental puzzle where you have pieces that fit together only in some specific or non-obvious ways. And usually it happens when we have large inheritance hierarchies or just overuse of design patterns. This is an actual example of what happens when we lose cohesion. And yeah, you can see we have very dense interconnection between these objects. And on iOS, they actually cause a retain cycle, which results in memory leaks. So we could set weak references, but that's a bit problematic because it's not actually clear which of these references would be weak. And yeah, so if we need to resolve this leak, we'll probably need to start refactoring this by removing the objects such as the parameter resolver and the value listener. And that will impact the interfaces of related objects like empty order at the top. So yeah, basically there needs to be some kind of balance between cohesion and coupling. But usually if an implementation has low cohesion, there are probably too many layers of indirection. And the way to fix it is, yeah, just by rewriting the code or doing some kind of refactoring. So the question I want to answer now is, yeah, can some code be reused, and how to aim at writing such code? And I think to answer the question, we need to think about two things: the purpose of the implementation and the context in which it operates. And yeah, basically this determines the applications and the dependencies that it has. So very often the question, so the answer would be no. So it just means that the code that we're writing is bound to a particular use case. And as an example, that could be some kind of a data query that we need for some specific report. And yeah, so let's call this kind of logic application logic. So that's fine, but sometimes part of the code could be useful for other purposes. So for example, we could have data structures such as the order objects that we talked about earlier. And they might be used when displaying data in different ways. For example, on the overview and detail screens. That happens very often. And yeah, so this kind of code, we'll call it domain logic. And then the other option is that it might also be possible to reuse a piece of code in other contexts. And in this case, there could be some useful behavior that can maybe be separated from its existing dependencies. And I want to call this code interaction logic. So yeah, I think it's useful to fit every piece of code into these categories, or at least try to do it. So application logic would consist mostly of transformations, and yeah, to fulfill the requirements for a new feature, yeah, it's just often necessary to combine the existing logic in new ways. So that's that will probably be part of the application logic. And here we really need to look for sequential cohesion. Then we have domain logic, and that will consist of entity definitions, basically. So you saw the earlier example of refactoring the order entry. And if we want to maintain cohesion here, we need to limit the behavior. So again, you saw earlier the example of refactoring that I showed. Basically, there we have definitions such as order type, order status, and the order protocol, and these would be all part of the domain logic. And so finally, we have the interaction logic, and that consists of functions or groups of functions. And if we want to achieve cohesion here, then the context must be provided from outside, and we need to carefully choose what are the parameters for our functions. And yeah, this will determine how composable the functions are and how testable they are. And basically, as we implement new features, there will be always opportunities to extract some common behavior out of them. And doing so successfully is what's going to result in more consistency and maintainability of the code. So these are the edit watch list and the order editor screens in the mobile app, and we've refactored them by applying the ideas that I've described. So there are also improvements in the design and the user interaction, and they make the UI much more responsive and attractive to use. Yeah, really the big difference is in the size of the implementations of the screens, which was greatly reduced compared to the older versions, and is much easier to make changes to. And yeah, I mean, making changes is something that we're interested if we're going to support the code base for a long time. So yeah, this is just a list of ideas that I think it's interesting to think about. So I have answers to some of these, but you know, some of these are also open, I think, to discuss based on the specific project and circumstances, of course. But yeah, I mean, in general, yeah, that's that's what I want to talk about, and I think it's useful to discuss these things a bit more in every project. And yeah, I'll be curious to hear your thoughts on this and or questions or comments. So yeah, thanks for listening.